So once again, good morning, everyone. So today we'll start the first chapter, which is about the load flow studies. So load flow studies is basically to know the network snapshot power flows on the network at a given moment. Okay, so if I pictorially represent the power system network like this. Now there are loads connected to the network, there are generators connected to the network, and this is the transmission network, and which has mainly the buses and the transmission lines connecting the buses like this. Okay, so the load flow study, as I said in the introduction class, that we are going to determine the bus voltages V1, V2, V3, and this is Vn. So we, at the end of the load flow study, we are going to find out bus voltages. Okay, now with that, knowing the bus voltages, we can calculate the line power flows both active and reactive power, and thereafter the overall network losses can be calculated. Knowing the bus voltage, we can determine these two, right? But ultimately the load flow solution gives me the bus voltages. Okay, now this is all about the network. The analysis is performed basically on the network, right? So this network is modeled or represented in two ways. One is nodal admittance form, which is actually I is equals to Y into V, right? And other one is nodal impedance form, which is a representation of the network in the form of V equals to ZI. Now here the vectors I and V are node voltages. Now this is I is the node voltages. Node voltages means bus voltages. In the sense, they are bus voltages, and I is the node currents. What do you mean by this node currents? Is nothing but the net injections into this node from the external elements, either generators or loads. Now what do you mean by this? This is node currents is net injection of current. Now net injection, I am saying particularly what do you mean by this net injection? Net injection means, see, you may have a generator and a load connected at a bus. There may be, right? So in a given big system, there are many number of buses. Few buses may be having only generators connected, few buses may be having only loads connected, like this, right? But few generators may have both generator connected and the load connected to it. This is load, right? This is load, this is load. Now this is generator and this is generator, right? Now the term net indicates that the Ig minus IL. Ig is actual amount of current feeding by the generator, and IL is the load current drawn from the node by the load. Okay, that is why I am putting these two are opposite to each other. This is injected and this is drawn. So net is Ig minus IL is the current which is actually feeding into the bus. And what about if I have only load? It will be minus IL here. It will be minus IL here. And what about if I have a only generator connected to it? Then it will be plus Ig. Okay. So this is the concept about the net current injection into the node. Current injection into the node. Now I have defined the vectors I and V. And what about this Y? Y is the Y bus. I say Y bus. This is node or nodal admittance matrix of the network. And what is this? Z? Z bus. This is nodal impedance matrix of the network, right? Now the same network can be represented in nodal admittance form and also nodal impedance form, right? Now depending upon our application of analysis, the nodal admittance form is more suitable for load flow analysis or load flow studies, right? Are you following this? Nodal admittance form of representation of this network is more suitable for load flow studies. That is why we try to form first the Y bus of the network. Okay, and the nodal impedance form of representation of the network is more suitable for fault analysis, fault studies. Okay, because you have already studied about the fault analysis. Okay, now I am actually in syllabus also you don't have the Z bus formation. Earlier I used to teach both Y bus formation, Z bus formation, load flow studies, fault studies and stability studies. That was the syllabus. Now the syllabus is slightly modified. Fault analysis I think you have covered already in previous semester. So Z bus formation we are not going to discuss in this syllabus, right? And moreover I am going to almost cover the entire syllabus from the power system analysis by Stevenson and Granger. I think I have shown this book to you. It will be blue in color. Okay, so try to have this book along with the other books also. So please read along with me as I proceed the subject. Okay, now you have got, now where we are now, I am talking about the bus representation. Before load flow studies, I am trying to represent my bus, and it can be represented in both, but for my load flow analysis I am going to represent only in the form of nodal admittance form, which is I is equals to Y into V, where I and V are the vectors of nodal voltages and nodal currents, and Y is the Y bus. It is called as nodal admittance matrix of the network. Now In addition to these two forms of representation, we also have a similar type of representation, but which are primitive in nature. They are called primitive form. We'll discuss about what is the difference between the primitive and the nodal form. So primitive form is also having two forms, that is I is equals to y v and v is equals to z I. So these are I and v vectors are now they are branch currents and branch voltages. Okay, you will come to know the difference between these two. For the time being, you make a note of that. The network can also be represented in the primitive forms, right? That is primitive admittance form of representation. This is primitive impedance form of representation, and these two forms can be written based on the mesh analysis, writing the equations in mesh and loop equations. Okay, right, where the currents and voltages are branch currents and voltages. Right now, these are actually the very basic old analysis. Very long back they used to do these manner, but as time progressed they try to adopt more convenient form for analysis, right? One is load flow analysis has the nodal admittance form, and fault analysis we have the nodal impedance form. Okay, right? So these are all the network representation. Now we are focusing only about the nodal admittance form, right? In nodal admittance form, we have I, y and v, two vectors and one matrix, and these are all the network parameters, that is all currents, voltage and admittances, all are network parameters. Okay, now only thing is I need to, if I have this y bus, then I can solve the equation given any bus or node currents. Okay, so I can solve for voltages. Given bus or node injections once I have the y bus of the network. Okay, right? So that is our solution. Load flow solution is solving for bus voltages, right? Now this is a simple linear algebraic equations, right? Linear algebraic, put it in the short form, in the vector forms, right? So once we have the y bus with me, once I have the y bus of the network, now given any node currents means these injections, net injections in my the network, then once I have those values, I can solve for voltages. Okay, now the question is how to form this y bus first. Later we can discuss about the solution of the network. Now formation of y bus for the given network, Now these can be done in two ways. Let me write here in two ways. One is direct inspection method, and other one is singular transformation method. right? Now, today we will take up the direct inspection method. If possible, singular transformation method, or otherwise we can deal in next class, right? Now, the direct inspection method is the method where you can form the Y bus by just looking at the network. By just looking at the network, you can directly form the Y bus. Okay, now that is very simple, straight away. But one drawback is there, that is, it cannot deal or it cannot be used in case the network is having mutual couplings. Okay, so there may be transmission lines, which are mutually coupled, right? Mutually coupled. Now, under that cases, the direct inspection method fails, right? Whereas the singular transformation method, which is actually Y bus is equals to A transpose Y primitive A. Now, this is the method which is used normally by the system engineers, okay, to study the load flow analysis of the network. Now, this can handle both with and without mutual couplings present in the network, and this is the most common method used by the system engineers, right? Okay, so we'll study both direct and indirect method. Yeah, now let us discuss about the direct inspection method. Direct inspection method. Okay, now let us do this by straight away taking one network and understand the Y bus formation. Okay, now I'll give a network. Now here actually we have a generator. Okay, so yeah, so this is bus number 1, bus number 2, bus number 3, bus number 4, right? Generator has some internal synchronous reactance. These are all line reactances. Okay, so if I okay, now this is network with line reactances. See, reactances or impedances, what it may be, right? Normally for the analysis, we try to neglect the resistances. We try to have only reactances for simplicity, but the same logic is applicable if even though the network is having the impedance resistance also. Okay, so if these are all the X values or Z values, reactance values or impedance values, right? Now I have to first convert this network to admittance form. The first step is convert this network to admittance form, right? So wherever the impedances are there, I'll take the reciprocal of that, and then I represent the line admittances, line admittances. Okay, right? And the generator is represented wherever the generator is there, it is equivalently represented by a current source. Its admittance, equivalent admittance, and this is the current equivalent current source, right? Now if I number the branches also, if I number the branches as well, so if I take this as YA, right, YB, YC, this is YD, this is YE, YF and YG, right? So branch A, B, C, D, E, F, G, right? So what is that I have done? Given any impedance network, I am trying to convert it as a admittance network. Okay, once I have done that, now simply write down the KCLs at each node. KCLs at each node. Okay, so yeah, so shall I write here? I'll write here. Now applying, okay, so applying KCL at node 1 node 1, this is, so there is no net injection here, we don't have net injection, 0, right? So this is 0. Now what are the currents we have here, right? So this is yeah, I have to define the voltages also. Let this is V1 voltage, this is V2 voltage, and this is V3 voltage, and this is V4 bus voltages. All these voltages are bus voltages with reference to this reference node. These bus voltages are with reference to this reference node, right? Now so this branch current can be written as, that is, this branch current can be written as V1 minus V3 multiplied by YC, right? So I have taken this as branch C, so this is YC plus V1 minus V2 into YD plus V1 minus V4 into YF. So this current, I am adding these three currents, summation to 0, because net injection is 0. Okay, so if you just bring all the coefficients of the each voltages, so I can have this V1 as YC plus YD plus YF, this and this, and V2 quotient is V2 into YD, V3 is there, V3 quotient is minus V3 into YC, and V4 is minus V4 into YF, right? This is equals to 0, right? So similarly, if you write down the nodal equation for bus 2, bus 3 and bus 4, right? So you have I am writing here, so bus bus 2 dagra, okay, applying bus 2, that is V2 minus V1 into YD plus V2 minus V4 into YE plus V2 minus V3 into YB is also equals to 0, because net injection into this bus is 0, right, equals to 0. So bringing all the voltage coefficients, V1 is there here, V1 is there here, minus V1 YD, and V2 is plus V2, and what are these coefficients? YE, here YD, and this is YB, right? And V3 coefficient, V3, where is that? Here, minus V3 YB, and V4 coefficient is this one, minus V4 YE is equals to 0, right? Okay, and you can write down the similar equation at bus 3 దగ్గర ఏమొస్తుంది? bus 3, so V4 with reference to, this is reference, right? Simply V3 into V3 into YA, this current, and what about, I am writing this current now, that is plus V3 minus V1 into YC, and this current plus V3 minus V2 into YB. These three currents should be equals to this current. Let us say this is I3, and let us say this current is I4, this current injection, net current injection, right? So this is equals to I3, right? Sum of this injection current is equals to the outgoing currents, this current, right? So if I write down again in the proper manner, that is V1 coefficient is minus YC, and V2 coefficient is minus YB, V3 coefficient is having plus V3 into YA, this is YC, and plus YB, and you have any V4? V4 is not there, so V4 is not there, this is equals to I3, right? Now similarly, if I write down the equation at node 4, so I have V4 into YG, this current going into this admittance, and what about this current? Plus V4 minus V2 into YE, and what about this current? Plus V4 minus V1 into YF is equals to this net injection, which is I4. Okay, so again rearranging, V1 is having minus V1 YF, V2 minus V2 YE, and V3 we don't have, V4 plus V4 into YG plus YE plus YF is equals to I4, right? So if I write down them in a matrix form, you have V1 here, V2, V3, V4, and its coefficient matrix is equals to the injection matrix. I1 and I2 are 0, I have only I3 and I4 currents, right? And what is the first bus equation? This is the first bus equation. So V1 coefficient is YC plus YD plus YF, V2 coefficient is minus YD, V3 coefficient is minus YC, V4 coefficient is minus YF into V1, V2, V3, V4, this into V1, this into V2, this into V3, this into V4 is equals to 0. That is the first equation I have put in the matrix form. Similarly, the next equation, if you write down the next equation, it will be coming minus YD plus YE plus YB minus YB minus YE, So this into V1, this into V2, this into V3, this into V4 is equals to again 0. Second equation. Similarly, third equation, minus YC minus YB, and you have here one term. This is YA plus YB plus YC, and this is 0. In fact, this is fourth V4 quotient is 0 here, right? So this into V1, this into V2, this into V3, V4 is 0 is equals to I3. Similarly, last equation, Y minus YF minus YE 0, and this one is, this element is YG plus YE plus YF, right? So you have represented the network in short, Y, capital Y into vector V is equals to vector I. Now what are the Y elements? If you notice Y elements, if I write down the Y bus as like this, capital Y11, capital Y12, capital Y13, Y14, Y21, Y22, Y23, Y24, Y31, 32, 33, 34, Y41, 42, 43, 44. Okay, now these elements, if you notice from here, right, all the diagonal elements YII, capital YII is actually the sum of, what are these elements? YC, YD, YF. What are YD, YC, YD, YF at 1? This is first bus. This is first bus. This is YC, this is YD, and this is YF. So that means capital Y11 is the sum of all the admittance connected to this bus. Similarly, if you see this one, second Y22 is DEB, Y22, so this is bus 2, B, D, E, YB, YD, YE, the sum of all admittances connected to this bus. So that means the Y bus elements, I am representing Y bus as this form, capital Y elements, and where the diagonal elements of this Y bus is sum of all line admittances connected to ith bus. I అని రాసాను ఇక్కడ. సో IJJ అయితే jth బస్ కనెక్ట్ అయినవి అలాగా. ఓకే, నౌ ఆఫ్ డయాగోనల్ ఎలిమెంట్స్. What are off diagonal elements? Yij. What do you mean by Yij? Line, this is line, admittance of line connected between I and J node, I and J node. So I normally represent the nodes like this here, 1, 2, 3, 4 nodes. This is 1, 2, 3, 4 node, right? Normally I represent, right? And it is a best practice to represent the nodes above the matrix like this in circular form, right? And in the figure also I have noted the node numbers 1, 2, 3, 4 in circular form, right? Encircling the node number. Okay, so what is this? If you notice this, the element yij, let me take ij, I equals to 1 and j equals to 2. Let me take I equals to 1 and j equals to 2. So what is that element I am referring to? Y12, capital Y12, this element. Capital Y12 is this element, right? So what is this element actually? from the above matrix, this element is equals to minus of yd. Where is this yd is coming? Admittance of yd. Yd is this one, and it is connected between node 1 and node 2. Node 1 and 2. So capital Y12 is actually equals to minus of small y12. Okay, I'm for this case. Similarly, I can write down here capital Yij is equals to negated value of admittance between I and j bus. Is that fine? Is that fine? Okay. Now this I can also write down sum of all admittances. Okay, so I can write down here y I j is running from 1 to some finite value small n, where this n represents the lines connected to bus I. Okay, now this is the short form of writing the y bus. Are you followed? Right? So directly y bus I can write down the diagonal elements equals to just add the admittance value connected to that bus, and off diagonal elements negate the value of that line connected between these two buses. Okay, now the small extension to this one direct inspection method is that now in this model, in this network, I have represented my line with a small with a series admittance or impedance. Are you following what I'm saying? In the above model, the line connected between the two buses I have represented by only a series impedance or admittance. So what do you mean by that? It is modeled as a short line. Now for medium and long lines, I have to represent it by a pi model. Is it right? Now in that case, right, in that case, what do every line should be represented as? If it is ith node and this is jth node, a line is physically a transmission line, medium and long transmission line are connected, then I have to model that line by a pi equivalent model having a transfer admittance or impedance and shunt admittance or impedances connected at the two nodes, right? Okay, now if I assume that the lines are now medium or long transmission line, in the same network, if I assume that the lines are now medium to long, now in that case I have to represent this by a pi model. Similarly, all transmission lines should be represented by its pi model. Is it right? So all transmission lines should be represented by pi model like this, right? Can you see these figures? So I am yeah, and, these transmission lines will have these shunt branches like this. Now this line is having a series admittance and two shunt branches connected, one at this node and one at this node. Similarly, this transmission line will have a series admittance and one shunt branch at this node and one shunt branch at this node. Now like that, all transmission lines will have their own pi equivalent models, right? Now if I apply the same principle and write down the KCLs at each node and put it in the matrix form, now what do you notice? Now if I write down, suppose if I write down the capital Y11, what is that actually? The formula saying that sum of all admittance connected to I, or here 1, it is 1. It is between 1 and 3, 1 and 2, 1 and 4, right? So you add up all the admittances connected to bus 1. Now here, in addition to the actual series admittances, in addition to the actual series admittances connected to this bus, you also have these shunt branches connected nearer to this bus. Yes or no? So y11 is equals to now yc, this value, plus yd, this value, yf, this value, and also these offline chargings. So this will be this line offline charging, that is yc by 2 prime. If yc prime is the offline charging, then by 2 is the yc is the line charging of line C, then by 2 is the offline charging. Similarly, plus yd prime by 2 plus yf prime by 2. So these elements are yc prime by 2 here and yc prime by 2 here. Similarly here, this element, this is yd prime by 2 on this side, yd prime by 2 on this side. Similarly, this is ye prime by 2 on this side of the bus and ye prime by 2 on fourth bus side. Similarly, this is yf prime by 2 on first bus side and this is yf prime by 2 on the fourth bus side, like that. Okay, so now while calculating the diagonal elements, you have to now add the offline chargings connected across the bus to the ground. Are you followed? Right? And what about the off diagonal elements? Is there any change? To this? చెప్పండి, ఆఫ్ డయాగోనల్ ఎలిమెంట్ ఏమైనా చేంజ్ అవుతుందా లైన్ చార్జింగ్స్ వల్ల?
No change, sir.
No change, right? That is what I want, right? So I can say in general, for any line, whether it is short, medium, long, right, with and without offline chargings, right? So the YII elements are sum of all admittances of the lines connected to ith bus plus admittances, line charging admittances. I'll say, I'll bit expand that, plus offline chargings. Let me say offline line offline chargings connected between ith bus and reference. Okay, is that clear? And yij no change, same, which is equals to minus of yij. This is small y and this is capital Y. Right? So direct inspection method is just by looking at the figure, I can form the diagonal elements, I can form the off diagonal elements. Right?